Hello and welcome to lecture 5 of using Newton's laws, and I'm just going to use this lecture to clean up a few more details, two details that are, important but not earth-shattering, and then one final detail that is very important. A subtle argument that often comes up is something that's called the massless string approximation. So let's say there's a box and we're pulling it across a surface using a string or a rope. And the free body diagram for the box, if there's no friction, would just be the normal due to the surface, the weight due to the earth, and the tension force exerted on it by the rope. Now, if you think about the rope, and if we neglect its weight, because it's got a low mass and so that should be small compared to the other forces, there's the force that we exert on the rope with our hand, and then it's tied to the box, and so there's a force that the box exerts on it. And that's really a tension. And in fact, Newton's third law tells you these are an action-reaction pair, because this is the force exerted on the box by the rope, and this is the box exerted on the rope by the box. So these have equal magnitude. So Newton's second law for the rope then is just taking right as positive, the force that you exert with your hand minus this force, which we just said is equal to T. And that has to be equal to ma, where that m is the mass of the rope. But if the mass of the rope is small enough, then this side of the equation is very, very small, and so the mass of the rope disappears, and we conclude that the force that you exert with your hand is equal to the tension in the rope. And so that means that the rope can be thought of as transmitting forces through it. Whatever force you exert on the rope ends up being exerted on the box. And this is called the massless string approximation, because notice that we had to make the approximation that m rope A was 0. So drag has come up a few times. Let's actually look at it in a little bit of detail. It's similar to a frictional force, but when an object has a frictional force acting on it, that frictional force is due to some surface that the object is in contact with. Drag is due to a gas that the object is moving through, such as air. A big difference between friction and drag, though, is that drag depends on the speed that the object is moving. And again, drag is a pretty complicated force. It's at least as complicated as friction, but there's a simple model that usually works fairly well. And here's the model. So the drag force is given by this formula, and that v there is just the speed, and note that it's squared. So drag increases quite quickly as the speed increases. That A is the cross-sectional area of the object. In other words, if you take the object and think of a cross-section sliced through it, what is the area of that cross-section? This symbol is the Greek letter rho. It's the Greek letter that says and it stands for the density of the gas that the object is moving through. And finally, this C sub d is called a drag coefficient. It's a property of the shape. And so this is what accounts for streamlined objects having less drag on them. Drag coefficients are typically around a half or thereabouts for a sphere, but they can be considerably higher for a very unstreamlined shape, and they can be below a half for sort of teardrop shapes and things like that. So a few things about drag. If you do a unit analysis on this, you will find that the drag coefficient is unitless. And so it's another thing like the coefficient of friction. It's a unitless coefficient. Let's just think about a baseball. And let's say you do sort of a soft underarm pitch so that v is, say, 10 meters per second. Then you can grind that v and the cross-sectional area of a regulation baseball and its and the density of air, and the drag coefficient for a sphere is about 0.5, and you're going to find that the drag is about 0.13 newtons. And if you compare that with its weight would be 1.45 newtons. So the drag at this sort of speed is less than 1/10 of the weight. That's perhaps not exactly negligible, but it is certainly small. Now, let's think instead about a baseball that you've dropped from a high building so that it gets going quite fast. Eventually, it'll be going fast enough and the drag increases as the baseball speeds up, that if you drop it from high enough, the weight and the drag wind up being approximately equal in magnitude. And so you can figure out how fast that would be if you just do the usual, which is Newton's second law, right? We're going to have a drag minus weight equals, and if they are equal, then that means that the net force is 0. And so this ball would be going at a constant velocity by this point. So that now says that the drag, that's a half CD rho A V squared equals mg, which means that the speed would be the square root of 2mg over CD rho A. And so that is then a special value of the speed that gets called the terminal speed. And so if you just drop the baseball, that's the fastest it's going to go. And so you can grind that through a calculator and find what it is for a baseball, but the important thing to notice is that the terminal speed is proportional to the square root of mass. And so high mass objects tend to wind up at higher terminal speeds if they fall far enough than low mass objects. Here's an example that illustrates several important points. Let's say we have Alice and Bob, and they're carrying out this experiment on a box. So before Bob got into this elevator, when Alice and Bob were both standing out just on ordinary ground, they've measured the mass of the box, and it's 10 kilograms. And Bob has now got into an elevator with the box and a scale, and the box is on the scale. And the elevator is now accelerating up at 5 meters per second squared. By the way, that would be rather uncomfortable for Bob. That's a bit of a high acceleration for an elevator. Anyway, the free body diagram of the box will have the weight, of course. And we know what that is. That's mg, right? So it would be about 100 newtons. And then there's an upward normal force. And the only thing the box is on is the scale. And so that's what's exerting this normal force. That is the only thing the box is in contact with. Now, let's take Alice's point of view. As far as Alice is concerned, the box is accelerating upward. And so she would certainly expect that the net force points upward. And in fact, she could check that because she knows the weight of the box. It's about 100 newtons. And the scale, well, what does a scale measure? You might be inclined to say that scales measure mass. But think about this. Hop on a scale. Look at what it reads. You don't have to tell anybody. And then if somebody comes over and presses down on your shoulders, you know that the reading on the scale is going to increase. But your mass hasn't increased, so clearly scales do not measure mass. What a scale actually measures is the normal force that it is exerting, or rather, equivalently, the normal force that's being exerted down on it. So Alice can determine what this normal force is just by reading the scale. And what she's going to find is that we can predict what that reading will be. The y components of forces are going to be n minus the weight. I'm just going to write that as mg, and that will equal ma. And so the normal force is going to be mg plus ma. mg plus a. Okay, and that's basically 15, and so that's 150 newtons. Okay, so greater than the weight of the box. And so that's what she should see on the scale if this scale reads in newtons, which is pretty rare, but you can get scales that read in newtons. All right, now let's take Bob's point of view. So from Bob's point of view, he agrees with all of this. Notice he knows the weight of the box, and he can read the scale just as well as Alice does. And so he knows these forces, which means he knows F net is up. So, however, notice something a little funny. For Alice, Newton's second law is working. But for Bob, he agrees, because he can measure the forces, that the sum of the forces is 150 newtons. But from Bob's point of view, the acceleration of the box is 0, right? Relative to him, it's not moving, and it's remaining non-moving. And so apparently, for Bob, the sum of the forces does not equal ma. So Newton's second law is failing from Bob's point of view. It works from Alice's point of view, but not from Bob's. So this is an important point. Newton's second law only applies from the perspective of observers who are not accelerating. Notice, Alice is not accelerating, but Bob is accelerating. And so if we take his point of view, and that means if we take his measurement of the acceleration of the box, then we expect that in his point of view, Newton's second law fails. So this is a very important point. If you intend to use Newton's second law to calculate something, then any reasoning you do about the acceleration of that thing has to be done from the point of view of a non-accelerating observer. The technical term used here is that Alice is in an inertial reference frame. Inertial reference frame. And that just means a reference frame in which the law of inertia, in other words, Newton's first law, applies. But in Bob's point of view, you see that there's a net force on the box, but it doesn't appear to accelerate. And so Newton's first law is failing for him as well, and so we call this a non-inertial reference frame. And Newton's first and second law only apply in inertial reference frames.